the first unit, we'll be dealing with the following information. This is for unit 1. Okay. That pressure is equal to force over the area, and that kinetic energy, here kinetic energy is for a gas, is equal to 3/2 kBT. kB is just a constant, okay, which was given to us in the beginning. I'll show you what that is. So kB is a constant, and capital T is temperature. That has to be in Kelvin, which is the same thing as half mv squared. You see how they here put VRMS? VRMS just means the average velocity. Okay, we also have anything over T is called the rate. So here Q over T means the rate of heat transfer, is equal to K, which is the thermal conductivity constant, and A, which is the area, and delta T, which is the change in temperature, over L, which is the length. We also have PV is equal to nRT, which you probably have seen it in chemistry as well, but PV is equal to nRT here will have different units. For example, in chemistry, we're taught that P has to be in ATM, but here it has to be in Pascal. V is the volume in chemistry, that's going to be in liter, but here it's going to be in meter cubed. N is the mole, R is a constant, okay, and R here is going to be a constant, which is 8.31, and the T is temperature, still in Kelvin. Okay, PV is equal, work is equal to negative PV. There has to be a negative in the equation. Okay, and oh yeah, also PV is equal to NKBT. So basically we can say that nRT is equal to NKBT. Now I can cancel the T's. I'll end up with NR is equal to NKB. Now KB is just a constant. Okay, let me show you what that is. So if you scroll back to the beginning of the equation sheet, it will give you what the KB is, which is that much. Okay. Now going back to that equation. So now we're gonna have that. Okay. And yeah. So what's capital N and what's small n? Small n is the number of the moles, but capital N is the number of the atoms. Okay. Now let's talk about capital U, which is the internal energy, is equal to 1.5 or 3/2 nRT, also equal to NKBT, which I think makes sense because here we see that NR is equal to capital NKB. So right now, if you replace the NR with N capital KB, you get the same thing. Okay. Finally, we have delta U is equal to Q plus W. Q is the heat, work is W. And then we have Q is equal to MC delta T if you're given two different temperatures, and C, which is a specific heat capacity. Then you can find the Q, which is the heat. These are the equations that you have to know for this unit. All right, now for the unit, we're going to have PV is equal to nRT. Okay, now this is applicable to ideal gases. What the book doesn't tell you is what are the properties of the ideal gases, and this always comes back in the exam. So they have multiple properties, which is that their volume is negligible. So their volume is going to be very small compared to the volume of the container. That when they do collide with each other, they collide elastically with each other, which essentially means that they will not lose any energy. No loss of energy. and they will move randomly, not in directional motion. Random motion. Okay, they will apply a force and they're going to apply a pressure on the walls of the container. And when they have a zero temperature, in Kelvin, of course, we're talking here, they will simply stop moving. They will stop moving. And if they can't move, they will have no pressure and they will have no collisions. And also, temperature determines their speed. So temperature determines their speed, and temperature determines their force of collision. Okay. So if we have a constant temperature, it essentially means that we have a constant speed. And if we have a constant temperature, we also have a constant force of collision. That means you will change the pressure, you can change the volume, it doesn't matter. If the temperature is constant, you have constant speed and constant force of collision. And so essentially, the force of collision is going to be directly proportional to the temperature. Okay, so far we have 6 properties. Number 7 is the property of the frequency of the collision. So force of collision is not the same thing as the frequency of collision. The frequency of collision is going to be direct with the pressure. So more pressure means more frequency of collision. Now, how do you define frequency of collision? Net force due to the collision. So frequency of collision is equivalent to net force of collision. Okay. Also, we have other things that we can talk about relationship-wise or proportionality-wise, which is the VRMS, which we already said is the average speed, is going to be direct with the absolute temperature. What's absolute temperature? It just means the Kelvin temperature. Okay. That the VRMS, the average speed, is going to be inverse with the square root of the molar mass. And finally, we can compare the VRMS, the average speed of 2 different gases. I can say the VRMS of gas A over the VRMS of gas B is equal to, open a fraction, the molar mass of gas B over the molar mass of gas A. See how I switch the places? If the VRMS of A is on top, the molar mass of A is in the bottom. Oh, okay. It's not a mistake. Okay. We also have another thing, which is that density is equal to molar mass times pressure over R times T. You have the duty of memorizing this equation.
Inshallah.
Yeah. So all of these things are not mentioned in the book. Okay. Are not mentioned in the book.
Yeah, actually, I remember I've seen a questions asking about these stuff.
Exactly.
Okay.
We still have more to go. Number 12 is that if you were to compare the speed of gas 1 or gas A versus the speed of gas B, this only tells you the speeds, but it does not tell you anything about the forces. Just because speed A has more doesn't mean force A is more. Please don't use logic in physics. That's number 1 rule. Don't use your daily life logic. Well, if this is this, then it makes sense of this. If once you say it makes sense, that means you're going to go in the wrong direction. Because if it makes sense without having an equation to back it up, then just don't even bother. Okay. So that's what you have to know about ideal gases. All right. Now, so PV is equal to nRT is the first equation to bother with here, right? Mm-hmm. And also we have kinetic energy is equal to half mv squared, or is equal to 3 over 2 kBT.
T.
So it seems that K is going to be direct with temperature, but V squared is direct with temperature. In the attempt of removing this square, we will square root both sides. So V is going to be direct with the root of temperature now. So what matters here is the two relationships here, that K is direct with temperature and that V is direct with the root of temperature. Okay. So that is important. Okay, so example 1 in the book. Look, we know by now that VRMS is direct with the square root of
The temperature.
the temperature. And so if the VRMS were to double, that means put this as a 2, the temperature would be, how would you save the temperature from the square root? You square both sides, correct?
Yeah.
So if you would square the 2, you get a 4, right?
Yeah.
So temperature had to go up by a factor of 4, essentially. Make sense?
Yes, yes.
Okay, let's do example 2. Okay, let's take it to a different space. All right, so we got a cylindrical container. Okay, and that's not a very good cylinder, but you get the idea.
Do we need to like convert the 15 centimeters?
You should always convert centimeters to meters. So now the radius is going to be 0.15
meter.
and the height is going to be 0.30. Let's try the given. The mole is 0.6 and the temperature is 433. How much force does the confined gas exert on the lid? So look, PV is equal to nRT. We know that pressure is equal to force over the area. That means if I know the pressure and I know the area, I can find the force. Yes. So now let me find the pressure. So P is equal to nRT over V. N is the 0.6. R is how much in physics? 8.31.
31, yeah.
You have to know that it's actually in the constant sheet. T is in Kelvin.
433.
Over V, which is the volume. What's the volume of a cylinder? Pi r squared h.
I need to apply these?
Yeah, but it's also given to you in the equation sheet, the volumes. So pi r squared h.
Okay.
Okay, let's see how much we get in the calculator. So I got 10.1809 Pascal. But of course I cannot put all of the numbers, right? That's too many numbers. There's something called significant figures. Have you heard of that before?
Yeah, I did.
Okay,
I
now
was about to ask, do we need the physics too?
we do, but there's a problem in the question. They never give you one significant figure. So it has to be like, there has to be like another one here. So 0.60. So how many sig figs do we have here? 2 is the least. Always go with the least. So our number here has to be upgraded to 1.0 times 10 to the power of how much? So I put the point here, and now I have how many numbers after the point? 1, 2, 3, 4, 5. 5 Pascal. So ignore the top one, just keep focusing on the other one. Now what's left is the force. Now force is equal to pressure times the area. Area is the cross-sectional area, which means the area of this circular part, which is pi r squared. Pi r squared, so 0.15
squared.
Okay. I got 7069 after rounding, but again, I should have how many significant figures?
2.
2. So I'm going to make it into a 7100.
Oh. Okay.
Because the zeros in a whole number on the right don't count.
Well, Mister, here's the thing.
Oh,
I
yeah.
got 2000, whatever. Okay.
Easy?
Yes.
Good. Okay, let's now talk about something called, and they love this one a lot in the MCQs, the Maxwell-Boltzmann distribution. Okay? Look, you can never have every single particle having the same exact KE. You can never. So if you see the word average, you will lean toward choosing that. They have the same average KE. That means that some have more and some have less, but on average they have the same.
Okay.
You can never have all the particles having the same speed, all the particles having the same energy. If that's a choice, never choose it.
Oh.
Just cancel it right away. Because some molecule will be moving faster and some will be moving slower. And if they're faster, they have more Ke. If they're slower, they have less Ke. So you will see this curve a lot in the exam. Now here it's a black and white. It's not very showy, but let me tell you what's going on here. Let's use a red color. So this is the 200 Kelvin. Mm-hmm. This would be the one that has been shifted to the right. So increasing the temperature will cause the reaction to shift to the right in terms of speed. But the hump has to go down. Okay, the hump will go down. So now the conclusion here is that more Ke means what? That the hump,
Shift down.
yep, is lowered, but the hump is moved to the right. The hump is moved to the right side to include more speeds. More Ke just means more speed. Now some will think that more Ke means double the speed. If you double Ke, you double the speed. That's incorrect, because Ke is equal to half mv squared.
Okay.
So v squared is direct with Ke. So ultimately v is direct with the root of Ke. So it's not a doubling effect. It's the square root of that too. Okay. And again, we use the word VRMS a lot. Get used to it. It means the average speed.
Okay.
So more Ke means more speed. There is nothing that is, new here. Okay, laws of thermodynamics. We have 3 of them in the book. The 0th doesn't count. The first counts. The second counts. The first and second come up a lot. The first law of thermodynamics just says that energy is conserved, which is the reason we have this equation. Delta U is equal to Q plus W.
Okay.
You know what Q is, right? Heat. W is work. Let's talk about the signs. So if the gas pushes on the piston, the gas is trying to expand. So its change in volume is positive. That means the work is negative. But if the surroundings push on the gas, you're going to be compressing the gas, which means the work will be positive.
So they're always opposite to each other?
Exactly.
Okay.
Exactly. That's number 1. Number 2, if the heat is absorbed, that means that Q is positive. If the heat is released, that means the Q is negative. What else? We have a couple of names that we have to get familiar with. So the word isothermal means that T final is equal to T initial. That means change in temperature is equal 0. And that means that delta U, the change in the internal energy, is also equal to 0.
Okay.
Because delta U depends on delta T. If that's 0, that one's also going to be 0. If we have adiabatic, that means the Q is 0. That means that there is no heat transfer. If they say there is no heat transfer, that means the Q is 0.
Okay.
If you see the word isobaric, what does the word isobaric mean? that means that we have a constant pressure.
Okay.
And that means you're going to have a horizontal line. If it's isothermal, you will have a line that's going to be concave up.
Okay.
Like this. And if we have volumetric, it's also called isometric. It's also called isochoric, where delta V
Zero.
is 0. And so the work is also equal to
Zero.
0.
Okay.
Oh, and adiabatic also has a concave up. Okay, but it's going to be less curvy. So adiabatic, where is it? This one. It's going to look like this, but less curvy. Okay. So that means that if I have a graph of P versus V, and if this one is the isothermal, then this one is going to be okay. Maybe not less curvy, but it's going to be lower than it. Okay. So here the blue one is the adiabatic, and the red one is the isothermal. Okay, very good. Let's speak about work more. Okay. How do you exactly find the work? So this is P and this is V. Work is going to be the area. So you might have to find the work in this area, which is just a rectangle. You might have to find the work in this area, which is now going to be a trapezoid. So finding the area is easy, but just keep in mind, as we go to the right, the volume is expanding. That means the work has to be negative. And if we go left, the volume is decreasing. That means the work has to be positive. Just keep the signs in mind. Okay. Also,
that's always the case, right?
Always the case.
Okay.
If you start and go back to the same exact point, that means we have an isothermal process. So delta U is equal to 0. Okay. If you have a vertical line, that means your volume has not changed. And if your volume has not changed, delta V is 0. That means the work is 0.
Okay.
Keep this in mind. Here, for example, I want to find the work from point A to point B. So that means I have to drag my lines to the x-axis, and I must find the area of this triangle and the area of this rectangle. Okay. So my work is going to be half by base. So that's going to be VB minus VA times the height, which is PA minus PB, plus the area of the rectangle, which is base or length times width, PB minus 0. You have to plus them. But don't forget, because you're going to the right side, your volume is expanding, your work has to be negative. So whatever work you find, just put that negative sign on it. Okay. Most of the exam is going to be in terms of letters, so just be careful. Okay.
So in this case, do I need to simplify more?
Yeah, of course, but I mean, this might come as MCQ already simplified for you, or FRQ might have numbers or something like that. Don't worry about the simplification, it's going to come later.
Okay.
And this equation is going to be very useful. It's useful in two instances. If you're given values, it's very useful. Or if your figure is just a horizontal line, you could just use that. You don't have to actually, find the area. If it's a horizontal line. So here, is our work positive or negative? As we go from A to B. Exactly, because as we go from A to B, my delta V is positive because my VB is more than my VA, which makes my work a negative. Yes. And if my delta V is positive, that means that the gas is expanding. So the gas is pushing on the piston. Okay, let's do example 3 here. By the way, here we have a closed pathway. You know what that means, right? If we go from A and return back to A, it's going to be isothermal.
Yeah.
But the question is not concerned with that. Now, the question now says, compare the work of path 1 to path 2. Now look, let's just look at path 1. So from here to here. That means what do? You will drag the points to the x-axis, and you will simply find the area of the shape, which is a rectangle. So you're going to do the base, which is 30 minus 10 times the height, which is 1.5 minus 0.7. I mean, sorry, 1.5 minus 0, right? To the x-axis. So you're going to have 20 times 1.5. Now, don't forget, it's 10 to the power of 5. It's 10 to the power of negative 3. We must also include those. So times 10 to the power of 5 times 10 to the power of negative 3. So you're going to have 30 times 100, which means 3,000 joules. That's the work for path 1. Let's now find the work for path 2, which is going to be dragging it from here all the way to here. You can do it as a triangle and rectangle, or you can do it as a trapezoid. It's obviously up to you, but trapezoid is going to be much easier for you. So the area of a trapezoid is going to be half base 1 plus base 2 times height. Now, some people are going to have a hard time telling what the bases are. The bases must always be parallel to each other. That's going to be base 1. That's going to be base 2 because they're parallel to each other. And the height is what connects them, which is that segment here from 30 to 10 or 10 to 30. So half base 1 is 1.5 and base 2 is 0.7 and the height is 30 minus 10, which is 20. But of course, don't forget that this power and this power. So times 10 to the power of 5 times 10 to the power of negative 3. Now we're going to have half times 2.2 times 20 times 100. That's going to be 2,200 joules. Okay. Oh, and also path 2, it says from A to D and then D to B. But then look, from D to B, it's only a vertical line. That means your volume is not even changing.
Yeah.
So it's going to have 0 work.
Yes.
So that's it. We found the work for path 1, found the work for path 2. Now what matters here is that we're both starting at A, we're both ending at B, but simply during different paths. And here different paths gave you different works.
Okay.
You know what that means?
Yeah.
The work is path dependent. So work is path dependent. That's what that means. Okay. Can you please do the math for PV is equal to nRT for the temperature? So T is equal to PV over nR. So P is 1.5 and V is the volume.
That's 10 times negative.
N is the mole.
0.6
8.31.
times 8.31.
How much do you get? So you got 300.84 Kelvin. But don't forget, there is a mistake in the question. You can never have 1 sig fig. That's total. They probably meant 0.50. So 0.50 here. You must only have 2 sig figs, which means you must say 3.0 times. Now look, ignore the 0.84. If you put the dot here, that means you have put 2 numbers on the right of the dot, correct?
Yeah.
You must have times 10 to the power of 2.
Okay.
That's your answer for Kelvin. which just means 300. Now, temperature at B. So now do the same thing, but just triple your volume, right? So copy paste your operation, but just triple your volume into a 30.
Okay. I got 902.
So just say 9.0 times 10 to the power of 2 Kelvin, right?
Yes.
Good. Now, C says find the work done by the gas during the process AB. So you're going to say work is equal to, it's just the area, right?
Mm-hmm.
But we're going right. That means you must put negative. Okay, now it's going to be, area, right?
Mm-hmm.
So 1.5 times 10 to the power of 5 times 30 minus 10 times 10 to the power of -3, right?
-3.
And you get the answer.
Mm-hmm. Yeah, 1.5.
-3,000. Okay.
Okay.
Now let's just fix the example 3. Again, we were going to the right side on both paths. That means we have to put negative in the end.
Okay.
Just don't forget that. That should be -3,000. The sign matters a lot. They're going to minus you big time. Now, part D says find the change in internal energy. That means you will do delta U is equal to Q plus W. Q is the heat which was given to us. Is this heat positive or negative if it's been added?
It's positive.
Positive.
Yeah.
So positive 7,500 minus 3,000. You get 4,500 joules.
Okay.
All right. Example 5. Look, if you compare example 5 to example 4, we have the same starting point and we have the same ending point. How do I know? Just look at the pressure and the volume in the beginning, and look at the pressure and the volume at the end. They're the same. And the rule says if you start and end at the same point, you're going to have the same delta U.
Okay.
So delta U is going to be not like work. It's going to be path independent. So delta U is path independent. Meaning, if delta U in this path, which was straight away from A to B, was 4,500, then delta U in the new path should also be the same. Which is how much? 4,000?
5,000.
4,500, right?
Yeah.
Okay. But now for the work is going to be path dependent. You must actually find the work. But question for you. How much is the work from A to C?
Do we subtract the one?
It's 0.
Oh.
It's a vertical line.
Right.
And how about from D to B?
Same thing.
So we just care about the work from C to D, pull them to the x-axis, and find the area of this guy. So we're going to have, it's going to go from left to right. That means it should be negative work.
Yeah.
Don't forget the sign. So negative, we have 30 minus 10 times 10 to the power of -3 times the height, which is 0.5, and times this power. You get -2,000 joules,
Okay.
I believe. -2,000 or -1,000. Okay. So -1,000 here. Now they want the heat, so we're going to say delta U is equal to Q plus W. 4,500 is equal to Q minus 1,000. So Q is equal to 5,500 joules. So if it's positive, is the heat added or removed?
Positive. Heat removed. Added.
Added.
Logic.
Yeah, but here in example 7, we're starting at A. We're going to go back to A. So what's the delta U?
Oh.
0.
0.
If you start at one point and you go back to it, the rule says that delta U is 0.
Okay.
The work done. How much is the work done from, let's call this C, let's call this E. From A to C, how much is the work done?
0.
Thank you. How about from E to D?
Same thing.
0.
Yeah.
So we just care about C to E and
A to B.
B to A. B to A.
Okay.
Now, C to E, is the work positive or negative?
Negative.
Because we're going to go and expand the gas, right? So it's negative work, but from B to A it has to be?
Positive.
Thank you. Which one do you think is larger, C to E work or B to A work?
Are they
Which one has more area?
C to E?
How? C to E is only this area.
Oh.
But A to B, the whole thing.
Okay.
So which one do you think now has more area?
It's B to A.
And since B to A is a positive work, that means our work has to be in the end positive.
Okay.
So look, since C to E is this, and A to B is all that, just count the square. Because they will cancel on the bottom part, correct?
Mm-hmm.
So how much is the area of the square?
It's I squared.
30 minus 10 times that. And then the height, which is 1, times that.
Okay.
2,000 joules. Easy?
Yes.
Now they want the heat. Delta U is equal to Q plus W. So 0 is equal to Q plus 2,000. So what's Q?
Negative 2,000?
Exactly. Not bad at all. Not bad. Example 8. Isotherm means temperature.
Mm-hmm.
State A from state A to state B, we have an isotherm. That means we have the same temperature. That's what they're saying. So temperature at A is equal temperature at D. Okay. So if temperature at A is equal temperature at D, did the temperature change from A to D?
No.
No. That means that this curve represents an isothermal process because temperature failed to change.
Okay.
Now look, they're saying that the work done is negative 1650.
Mm-hmm.
How much is the heat? And the whole thing is isothermal, right?
Mm-hmm.
So delta U is equal to Q plus W. Delta U is 0. And the work is negative 1650. Q is
50.
Heat is absorbed or released?
Heat is released.
It's positive.
Observed.
Absorbed. Now the second law of thermodynamics is going to be very important. It says that heat will flow spontaneously from the hotter object to the colder object. Why? In the attempt of increasing entropy. So right now, if you put those two gases together, gas 1 and gas 2, once they mix, you get disordered state. And if gas 1, say, has a temperature of 500 Kelvin, and gas 2 has temperature of 300 Kelvin, which one is going to lose heat? Which one is going to gain heat?
Gas 1 will lose.
Right.
Gas 2 will gain.
And they will distribute until they reach what we call thermal equilibrium.
Okay.
Which means they must have the same temperature at some point, but the entropy of the system has increased by putting the two gases together. That's important. Okay? Entropy has increased. Okay. So heat will always flow from the hotter object to the colder object spontaneously until they reach thermal equilibrium. You must memorize these shapes, okay? So isothermal will look like that. Isobaric will look like that. Isochoric or isometric or isovolumetric will look like that. Adiabatic will look like that. You have to know what they mean.
Well, Mr. Like, in one of the examples, there were like this and then this and this. Do we count it as like constant pressure and volume or no?
Just look at the line. If it's a vertical line, it's a constant volume. If it's a horizontal line, it's a constant pressure.
Okay.
If it's not, one of these is not then.
Okay.
AP question. If you want to achieve a constant volume, you must say we have to lock the piston in place. So look, PV is equal to nRT. You want to increase the pressure. So P is going to be inverse with V, but direct with temperature. But they just said achieve a constant volume. That means that volume has to be removed from the equation. So now pressure is going to be direct with temperature. So now if you want to increase the pressure, you have to increase the temperature.
Okay.
How would you do that? By using a warm water bath.
Okay.
Now, again, to achieve a constant volume, you must lock the piston in place. And now if you want to decrease the pressure is going to be direct with temperature. That means you must now use a cold water bath.
Okay.
Okay. Now you want to hold the volume constant, right? And you're saying discuss how the temperature of a gas in a cylinder is decreased upon a drop in the pressure. Okay. So the temperature of a gas in a cylinder is decreased upon a drop in pressure. So look, PV is equal to nRT. You're holding the volume constant. That means that P is direct with
Temperature. Okay.
So how would the temperature of a gas in a cylinder drop? So let's say you have put a hot gas at 500 Kelvin in a cylinder. How would the temperature dissipate away from the gas? Because the gas has more heat, so the particles are faster, and they will collide with the surroundings, which are slower, right? And the heat will dissipate. It's like having a hot cup of coffee. It's not going to be hot forever because the heat will be lost to the surroundings over time.
Okay.
Which is, by the way, consistent with the second law of thermodynamics and the attempt of increasing the entropy.
Okay.
Okay. And if you ever come across isothermal and adiabatic in the same graph, isothermal always has to be on top.
Okay.
Always has to be on top compared to the adiabatic. Also, they love these words or these phrases. If the piston is pushed in or pulled out slowly, that means that delta U is 0.
Okay.
But if the piston is pushed in or pulled out quickly, then the Q is 0.
Okay.
So please keep that in mind somehow. Slowly means delta U is 0.
Quickly, Q is 0.
Quickly, okay, I like that. Quickly starts with Q. So Q.
Okay.
Okay. There are 3 methods of heat transfer from hotter object to the colder object. Conduction requires the physical touching of the two objects, where the hotter object will give its heat to the colder object via collisions. You have to have collisions. Okay. We also have the second way of transferring energy, which is by convection. But this one requires the movement of a hot fluid. And the fluid here means liquid or gas. Like in the summer when you have the heater the heater is making the air around it hotter, which will then, now look, if we have more temperature, the density will decrease.
Yeah.
That means the hotter air is going to rise. And as the hotter air rises, it will get, let me use red for hotter, it will get replaced by the colder air because the colder air has more density. So that means the hotter air has less density, but the colder air has more density.
Okay.
And this will keep happening until the entire room is hot. Now, the third method of heat transfer is called radiation, which means the sunlight or the flame of a fire. But radiation is able to travel in a vacuum. So whenever you see vacuum, know that it's what? It's radiation.
Okay.
Because space means a vacuum, the sun's energy can travel in a vacuum. Now, the second law of thermodynamics is loved in the MCQ, like very loved. And only these points will come up. Ready? Yeah. The total entropy of the isolated system can never decrease. Mm-hmm. And it will only increase until it becomes constant, which happens to be at thermal equilibrium.
Okay.
Okay. Now, entropy of a closed system can never decrease, but the entropy of an open system can decrease. And when the system moves toward thermodynamic equilibrium, that means that entropy of the system will increase. Entropy is going to be the highest at thermal equilibrium.
Okay.
And the closed systems spontaneously move toward thermal equilibrium.